We know that ARIMA models involve choosing the order of integration, order of autoregressive and moving average lags. It is one of the most important steps in the ARIMA model specification. In this tutorial, we will illustrate how plots of variables, autocorrelation function and partial autocorrelation function plots can be used to get insights into the order of ARIMA models. The autocorrelation function or ACF shows the correlation between the time series and its own lagged values. It is the correlation coefficient estimated between the series and its past values. For example, ACF at lag 3 is the correlation between a time series yt and the same time series lagged by 3 time periods or yt-3. This way, we can estimate ACF at all lags and plot them on a graph showing the correlation coefficient at each lag. Partial autocorrelation function or PACF, on the other hand, controls for the effects of other lags when estimating the correlations. It is often done using linear regression. The PACF at a certain lag is the coefficient of that lag after controlling for the lags in between. For example, PACF at lag 3 will be the coefficient at lag 3 after controlling for lags 1 and 2. We can run different regressions with different lags to obtain PACF values and plot them on a graph. We will illustrate how to use these ACF and PACF plots to decide the order of ARIMA models. First, let us talk about how to decide the order of integration, differencing, or D. It is always a good idea to plot the time series variables. Even basic plots can give us insights into the behavior of the time series variable. If we look at the first plot here, the variable does not look to be stationary. For forecasting with time series variables, stationarity is an important property to have. The order of integration refers to the number of differences it takes to make the variable stationary. Since this variable does not look stationary, this is the first sign that we might need to take differences. We can also see this in the ACF plot shown here. When we see a slow decline in autocorrelations with increasing lags and the autocorrelations are significant for a large number of lags, it usually indicates that we need to increase the order of differencing. In our example, ACF is declining gradually and the autocorrelations are significant even at higher lags. This is another sign that we need to consider a higher order of differencing. Moreover, we can see that the first lag of ACF is almost equal to 1, which also indicates that we have to increase the order of differencing. Since we saw that we need to increase the order of differencing, let us take a look at the plots of the variable at first difference. In the first plot shown here, we can see that the variable looks a lot more like a stationary variable after taking the first difference. If we look at the ACF plot at first difference, we can see that the autocorrelations are no longer significant at higher lags as we saw earlier. Here, only first 4 lags of ACF are significant and they are gradually declining. The first lag of ACF is about 0.3, which is nowhere close to 1. We could consider increasing the order of differencing if this first lag of ACF is close to or equal to 1. Both these plots indicate that taking the first difference should be enough and we can move ahead with the order of integration D is equal to 1. When we are deciding the order of integration or differencing, we must be careful and avoid overdifferencing because it can lead to loss of information and inaccurate forecasts. Let us assume that we decide to take the second difference in the example we are considering. If we look at the plot of the variable at second difference, the series now looks to be stationary. However, this can be deceiving and we must take a look at the ACF plot. The ACF plot now shows a negative and significant autocorrelation at lag 1. The coefficient is almost equal to -0.5. Moreover, we can observe that the ACF are changing signs from positive to negative and negative to positive in the higher lags. Both these things indicate that we have overdifferenced the time series variable. A mild case of overdifferencing can be corrected using additional moving average or MA lags. However, we should reduce the order of differencing if the first lag of ACF is close to -0.5 or more negative. In our example, the first lag of ACF is almost equal to -0.5 and we should reduce the order of differencing. Therefore, our earlier decision to go ahead with the first difference looks to be correct. Now that we have decided on the order of integration, we have to decide the order of autoregressive and moving average lags next. We can use the ACF and PACF plots to decide the order of autoregressive and moving average terms. We have to plot the ACF and PACF at the chosen order of integration or differencing. For instance, if we determine the order of integration or D to be 1, then we have to estimate and plot the ACF and PACF at the first difference of the time series. The behavior of these ACF and PACF plots at different lags gives us insights into the appropriate order of AR and MA terms. Suppose the ACF and PACF plots at the chosen order of integration look similar to the ones shown here. This behavior is typical of an AR or autoregressive process. We can say that based on the patterns of ACF and PACF plots. In the first plot of ACF, we can see that the autoregressions are declining gradually with lags. At the same time, the second PACF plot shows some significant lags followed by a sharp cutoff. This shows an AR signature where ACF is gradually declining and PACF is showing a sharp cutoff. We can also decide the number of AR lags based on these plots. The number of significant lags in PACF before the sharp cutoff shows the number of AR lags or order of AR. In the PACF plot here, we can observe that the PACF cuts off at the third lag and the first two lags are significant. Therefore, we conclude that 2 AR lags is a good starting point and we can estimate an ARIMA 2D0 model. The behavior of ACF and PACF plots is reversed in an MA process. The ACF and PACF plots shown here exhibit a typical MA process. The second plot of PACF shows a gradual decline with lags, whereas the ACF1 is negative with some significant lags followed by a sharp cutoff. Similarly, we can also decide the order of MA terms based on the cutoff and the number of significant lags in ACF. In the ACF plot here, we can see 2 significant lags and a sharp cutoff at the third lag. This indicates that we should use 2 MA lags and MA2 is a good starting point for our model. Hence, we can start by estimating an ARIMA 0D2 model. Usually either AR or MA terms are enough to model a time series. However, this may not be the case every time. Sometimes, a combination of AR and MA terms gives the best results. In the ACF and PACF plots shown here, we cannot see any clear cutoff in either the ACF or PACF plot. Both ACF and PACF are gradually declining with lags. This indicates that we might have to use a combination of AR and MA terms in the model. However, we must be careful when including both AR and MA terms. The AR lags act as a partial difference, whereas the MA lags cancel out the partial overdifference. This means that the AR and MA terms can sometimes interfere with each other and cancel out each other's effects. If a model with both AR and MA lags seems to be working, we should still check the alternatives by decreasing the AR and MA terms. This is essential to ensure that the AR and MA terms are not interfering with each other. Suppose an ARIMA 2-1-2 model seems to be working well. Still, we should try estimating ARIMA 1-1-2 and ARIMA 2-1-1 and compare their results. This also brings us to another important aspect that we must keep in mind. In an ARMA process, we must first consider the minimum number of AR and MA lags and gradually increase the AR and MA terms. We should not start by estimating an ARIMA model with a high number of AR and MA lags. If we observe that a combination of AR and MA terms is needed, start by estimating the ARIMA 1-D1 model and increase the number of AR or MA terms only if needed. Another approach to choosing the order of ARIMA models is with the help of information criteria. In this approach, we estimate several ARIMA models with different orders of integration, orders of AR and MA terms. From these estimated models, we can calculate the values of information criteria such as the ACF information criteria or AIC, Schwartz information criteria or SIC, or HQIC. Then, we compare the values of these information criteria for different ARIMA models and choose the model that has the minimum value of information criteria. For instance, if we are using ACF's information criteria or AIC, we will select the ARIMA model that has the minimum value of AIC among all the models. This works because these information criteria penalize the inclusion of extra and unnecessary variables or lags. The drawback of this procedure is that we have to estimate a lot of ARIMA models and then also estimate the information criteria for each. This can be a time-consuming process. However, some software programs provide functions to automate this entire procedure. For example, the auto.arima function in the forecast package of AR can be used for this purpose. It automatically estimates the information criteria for different combinations of AR, MA and order of integration and finally chooses the ARIMA model with minimum values of information criteria. Another approach we can take is to use the ACF and PACF plots to get a starting point for the order of ARIMA models, which will narrow down the number of models to estimate. We will illustrate these approaches in the upcoming tutorials. When dealing with ARIMA models, there are a few more things we must watch out for. First, we already discussed the problem of overdifferencing earlier. If the ACF of lag 1 is more negative than -0.5, then the series has been overdifferenced. We must decrease the order of integration or differencing in that case. The second important question to address is whether to include a constant in the model or not. If the order of integration or D is 0 in the ARIMA model, we usually include a constant to allow for a non-zero mean. If the order of integration or D is 1, then including a constant depends on the time series under consideration. Using a constant in first differences allows us to incorporate a linear trend in the original variable. If the order of integration is 2, we usually don't include a constant. This is because a constant after the second difference implies a trend in trend and a quadratic type of trend in the original time series. This can be problematic when we have to forecast over longer periods. When we estimate an ARIMA model, we must also watch out for a unit root in the AR and MA parts of the model. If the AR coefficients or their sum is equal to 1 or very close to 1, this means that we have a unit root in the AR part. In this case, we must increase the order of integration or differencing by 1 and reduce the AR lags by 1. Similarly, if the MA coefficients or their sum is equal to 1 or very close to 1, then we have a unit root in the MA part of the model. Here, we must decrease the order of integration or differencing by 1 and also reduce the MA lags by 1. Earlier, we also mentioned that we must be careful when using a combination of AR and MA lags. This is because they can cancel out each other's effects. Even if the AR and MA coefficients are statistically significant in the results, we must be careful of this. If the ARIMA model is taking long to converge with more than 10 iterations, then it indicates that the AR and MA terms might be interfering with each other. Thank you for watching, and I will see you in the next tutorial.